unaccelerated system-level CPU verification through simulation-emulation coexistence. Abstract. The most significant hurdle currently for design verification is the long simulation time to functional and low-power scenarios of complex design at the SoC level. This huge simulation time arises due to the addition of the multiple heterogeneous process cores and graphic processors and accelerator, several prefers and DDR and etc., and makes iterative debugging a time-consuming and sometimes insufficient task. While the simulation is suitable for the software arrangement that tries to mimic all the actual conditions, so emulators are one step closer to this aim, with almost the whole target device virtualized. Hardware emulation is the technique of prototyping real SoC design and accelerating the speed of the design execution. This methodology presented in this paper has the potential to be scaled up various platforms across different changes like automotive SoCs, mobile SoC, and wearable SoCs, along with the uniqueness and complexity in order to uncover bugs related to low power functionalities, and testing involves traversing through the multiple power up and power down sequences, and hence these scenarios are best suited for testing on emulators. Some of the other long-running cases that could potentially reap the most benefits are coherent scenarios which involve the real RTL of GPU or other multimedia blocks along with the real CPUs. Hence, this paper targets bridging the gap between design and time to market using coexisting simulation and emulation methodology, and works through some novel approaches that cover stress areas of functional verification. Introduction. The hardware-assisted verification or emulation deliver capacity and performance for extreme fast, full systems on chip testing. So emulation enables testing of a large number of long-running test cases in a fraction of the time consumed by simulation. In doing that, it also allows more design requirements to be covered while more bugs are uncovered. For the purpose of this paper, we have done extensive testing of functional scenarios spanning from the coherency to dynamic voltage and frequency scaling to power over a range of various low-power scenarios, which are very critical for a competitive SoCs at these times. Since the emulators are running at actual clock speed and each hardware component, FPGA on-chip memory and off-chip memory are running at megahertz speed, the throughput of a design becomes really high and the overall verification life cycle is speed up. So figure 1 below shows a high-capacity system emulator with the hardware blocks associated with it, and the server, the DUT, design under test. DUT is mapped on one or several FPGAs and memory chips. The test environment is mapped onto dedicated FPGAs, interface FPGAs, as which implemented the hardware test bench. The emulator server unit is connected to the host PC through a high-speed interconnect board. The figure 1 is hardware of emulation platforms. The 2 is the emulator compilation. The compile, as depicted in figure 2, starts with the original register transfer level RTL code of the design and automates all of the necessary steps to synthesize and map the design for given emulator hardware configuration. The emulator compilation has 4 stages: front-end, system-level back compilation, and core-level back-end compilation, and FPGA place and route. The first stage synthesizes the RTL source files to generate gate-level netlist, system-level backend compilation splits, extra large netlist into medium-sized netlist, and perform the system-level place and route and static timing analysis, generating the appropriate database for run environment. The compilation maps medium-sized netlist onto emulator server, and FPGA place and route creates the binary files for the FPGAs. The choice when creating the compilation project are important because the correct compilation project makes design verification easier. An optimized compilation balances the compilation efficiency and emulation performance. Figure 2. Emulator compilation flow. Section 3. Related work. The power-aware verification of SoCs has been around for a decade ever since IEEE released the UPF standard. Only with as 1, 2, 3 laid the foundation of simulation-based power-aware verification of system-on-chip. Since then, the advances were made by industry partners to streamline the UPF verification flows. Today, we not only have a multi-core SoC design, but also multi-users SoCs with dual architecture processors. We do not have a processor implemented on the same die. Needless to say, this increase in complexity due to the SoC architecture evolution has shipped up into the requirement of the power of verification and is fast becoming the long pole of the verification life cycle. To showcase the results obtained in this paper, we divided the power-aware verification requirements into a number of test categories and a successful accelerated power-aware verification life cycle with the use of emulators by incorporating UPF design libraries and power domain control into design images used for emulation-based verification. So that this has resulted in up to 40 times saving in the time and resources. Chapter 4 is fundamental methodology. The A, test planning and test priority. A diligently made test plan gives greater product predictability, more aggressive innovation, and handles late-stage spec changes. Keeping this in perspective, we prepare our test plan in such a way that critical and long-running functionality like lower power scenarios, random stress traffic, etc. are targeted to run an emulation platform in order to give faster results. Due to the certain limitation in emulation, such as missing checkers or difficulties in debug, such cases could be recreated on simulation easily. During the verification cycle, the test plan will usually go through several reviews and needs to be approved prior to the execution. After the test plan is completed, it will go through the test prioritization. Setting the test priorities is now really a simple task, and great responsibility lies on getting the priorities right, since the priorities set the order of the test plan, execution, and debug. Our aim is to categorize the tests and their priorities such that verification milestones are not blocked due to the runtime of the sum of the important scenarios. B. Migration to emulation. Figure 3. Basic steps of migrating a simulation run to emulate. Initially, a few basic sanity tests are run in the emulation and is carried out via a step-by-step process where the setup that needs to be done before the actual emulation run is brought up. Once the scenarios are identified as emulation closer items, their C image files are generated after compile, similar to a simulation of C code. As per the steps shown in Figure 3, the verification engineers need to be identified which functional scenarios needs to run in which environment. Once identified, a variety of mixed functionalities are run on both simulation and emulation for comparison of the runtime. Starting with the desired scenarios which needs to be run, we compile the C-test and generate an image file which can be either run on full image of base image depending on the blocks involved, using certain script to generate or separate the binary file with the design data and using ticker file for the rest of the setup changes. The run is launched on the emulation platform. The C enhancement are done. In addition to migrating the complex scenarios of SoCs to emulation, this paper also targets to automate the processing of migration in order to improve the efficiency. As shown in Figure 3, the separation of binary files, in case of the full image, application for license and start and stop of the waveform dump, or required environment of the user. All these steps are automated and to make into a single input and single command scheme. Section 5, the coherency scenario on emulator. Figure 4 is typical complex SoC and a complex coherency scenario. Understanding the fact that a processor vendor may not provide a coherent connection, mechanism for multiple clusters and a system-level cache coherency is fundamentally has to verify. We tried to create the complex coherency scenarios in SoC level since we are connecting multiple clusters together and each core in each cluster will have their own private L1 and private shared L2 and caches and shared L3 caches. In addition to this, there can be a single level cache or a last level cache on the system, hence adding thorough the requirement for coherency testing at full chip. We successfully created stress scenarios using varying traffic such as DVM, exclusive accesses, IO current transactions, and etc., which is an ideal candidate for emulator 1. So we also verify page table properties and memory ordering in these scenarios and created multiple cache line evictions. So section 6 is dynamic voltage and frequency scaling scenario. Figure 5 is the dynamic voltage and frequency. Now we all know the DVFS. There is no DVFS stand for. Just provide ways to the reduce power consumption of chips on the fly. Different design blocks at SoC work at a different frequency, and verification teams has to traverse through all the voltage and frequencies for testing purpose. But at the same time, it's important to note that the testing scaling of frequencies for memory interface, cores, coherent interconnect, and etc. It takes a huge simulation time. Hence, we created and run these scenarios on the emulator platform in order to gain significant confidence in our DVFS. Figure 6 is the different blocks of SoC operating on different voltage clock. Chapter 7, Low Power Scenarios. We tried to run various low power scenarios in emulation level like core and cluster clock gating schemes, memory retention schemes, as well as complete power down and sleep scenarios for various blocks of SoC. The figure 7 on the right shows different processor states possible and the waveform in the figure 8 shows a typical power down scenarios for cores and cluster which can be verified using emulator in an efficient manner. These low-power scenarios are also in a power-aware setup with the UPF incorporated. The entire methodology to enable the power-aware runs is explained in upcoming sections of this figure. Figure 7 is power state transition. Figure 8 is power down mode for the cores and cluster. So section 8 is UPF enables and a compilation flow. A. Enable UPF-based power-aware run on emulator. This methodology ensures that all synthesizable design components are reused between the PA-simulation and PA-emulation design targeted, thus the enabling consistency of the testing between PA-simulation and the PA-emulation test environment. This means that now we can use both platforms to complete each other in the verification life cycle with a high degree of confidence. Further in the paper, we shall see how we have efficiently offloaded long-running power-aware scenarios to PA-emulation environment to bring down the testing time to a fraction of what it was in the PA-simulation environment. The topology of the power network is described by the UPF script for the design and is an input to the compiler. The emulation compiler chooses support the following stage of UPF Unified Power Format version: UPF 1.0 and UPF 2.0 IEEE 1801-2009 standard. Limited set of commands from a UPF 2.1 IEEE 1801-2013 standard. The compiler chosen also support both hierarchy and non-hierarchy UPF. Hence, inside of UPF files, the hierarchical path can be declared and applied. Like this. Figure 9, a sample UPF code describing power intent of the design. B. Compiling a PA power-aware emulation design test. The first step is to make file changes and identify the compilation options that need to change for the running lower power scenarios. While compiling, we need to fix any errors that come to any power-related ports for any IP instances. We also need to ensure the availability of the complete list of UPF libraries to be included. Next step is to use the available utility to convert present libraries to emulation-compatible libraries. After that, we can run live to DB convergence script and convert libraries to the format needed. After all of this, once we fix all the UPF compilation issues and related to the version or any specific tool option, we can run on our basic single or multi-core power down scenarios and verify that the intent of the test has been achieved. So next one is figure 10 is methodology of running PA power-aware runs on emulator. C. Power-aware compilation flow on emulator. As shown in the figure 11, below the both UPF files and RTL files are fed into the EDA tool, which can understand the power intention of the design through UPF files and functional intent from design files. After the process of the analysis, elaboration, and speed splitting, and then synthesis, and EDA files are produced, which are vendor-neutral file format used to store netlist. The power-aware emulation model compilation flow presents to us with the following advantages: the common semantics and the analysis between the simulation and emulation model and target. Similar UPF constructs are supported between simulation and emulation environment. And early error flagging the capability of simulator tools are leverages. precedence rules and implementation carried over from the simulation targeting. The debug continuity across the PA power-aware simulation and power-aware emulation. So this is the figure 11, a unified compilation flow for hardware run. The important commands and APIs used for UPF enablement. Figure 12 below illustrated the important UPF commands that are leveraged from a PA-sim target power intent. The figure 12 is a list of important UPF commands and their usage. And the emulator also provides a set of C++ APIs through the class PowerMGT that seamlessly enable power-aware verification on emulation. And the below table, some of the important members of the PowerMGT class are discussed. This is a figure 13 important C++ APIs used during the PA run. And then the Section 9, common errors are faced and their solution. The clash of rules and design attribute among various IPs. One of the most frequent errors that we faced during model compilation is the enabling and disabling of a power well bias varying from one IP to another and clashing with the power bias enabled and disabled rule at the SoC level. To resolve this, we had set the enable underscore bias to force the all IPs and for all IPs and the SoC top. The figure 14 is the most frequent error during model compilation. Number C is the corruption cell libraries. The cell libraries for various IPs and vastly different release schedules and enhanced during integration, and sometimes we end up the wish stale with the corrupt library paths which need to be updated manually. So that is a figure 15 error due to the corruption cell libraries. Section 10, result and conclusion. Result 1 is this paper demonstrates how multiple long scenarios can be smoothly ported onto an emulation platform and is much easier and faster than simulation. Number 2, the experiments were carried out for several functional and low power scenarios along with the simulation for the same scenarios and the design drop for comparison. 3. The runtimes were recorded and analyzed. The corresponding plots are shown in figure 16 as an indicator of the result. 4. By using this method, we significantly reduced the number of iterations needed, debug time, and the verification schedule. Current results are indicative and based on 2 emulator platforms from vendors like Cadence and Synopsys. However, with the latest version platforms, and the benefits of the observed are furthermore. 5. We also narrowed down the areas of the critical bugs, since we specifically aim to find relevant bugs early through this environment and not the complete coverage. Further enhancing the process by the adding automation, verification engineers can maneuver between the two environments very easily as per the requirement. The result achieved in some of the Exynos mobile SoCs and automotive SoCs were demonstrative of the fact that we saved at least 50 times enclosure to certain critical long pole features. Figure 16 is non-power result across the 2 platforms. Figure 17 is power-aware run result on a Synopsys platform. And that is reference is, I think, 11, section 11. Okay, good. Today, I read this paper on accelerated system level CPU verification through the simulation-emulation coexistence. Thank you for your time and see you next time.